degradation. Okay, we have now with us Alessandro Virtuani from EPFL. He's a senior researcher, and he will talk to us about something also very important for any module, but in particular also for heterojunction modules, and that's the packaging structure, which they have improved to extend the reliability and durability. Alessandro, the floor is yours.
Okay, Michael, thanks for the introduction. First of all, do you hear me? Yes, I do not hear you any longer. I will now share my screen. Okay, so
can you go to presentation mode?
Yes, but generally it's enough to, let me check. Okay, so you also see my screen now. Good, so I will talk about packaging structure for silicon heterojunction solar cells modules. And this is briefly the outline of my presentation. So I will, this is a common buzzword, that of targeting 30 or 35 years of PV module service lifetime. I will make a very quick jump in the past and show you that in principle, this is a reachable target. Then I will focus on the silicon heterojunction technology and try to understand what are typical degradation rates for the long-term performance of silicon heterojunction modules, and even try to highlight if there is any peculiar weakness of this technology or failure modes which we need to really have a look at. And then I will jump to the final part of my presentation, which is really talking about this, I call them reinforced module structures for silicon heterojunction solar cells. So as said, the issue of targeting a service lifetime of 35 years is really hot topic in PV right now. And let me make a jump in the past. So this is a work we have published 2 years ago and also presented to EU PVSec. And it was the first grid-connected PV plant in Europe, which was connected to the grid in 1982 in Lugano in southern Switzerland, which has a temperate climate. And what makes really this plant a kind of unique of its kind is that the history of the plant was extremely well documented with regular measurements, indoor laboratory measurements of the modules. And during 35 years of operation, everything in the PV plant changed. The location, you can see 2 different locations. So the plant was moved from one roof to the neighboring roof. The inverters changed 5 times, also the monitoring system, but only one single component of the module never changed, and that's the original set of nearly 300 modules. You can see on the right-hand side how these modules were looking like. They were Arco Solar modules, so manufactured in the US, 36 watts, relatively conventional 4 inches crystalline silicon technologies, relatively thick, and with a very robust module structure. So these modules were made, of course, with glass, but they had a very robust backsheet, which was a Tellar metal Tellar sandwich, plus also an edge seal. So basically, this structure is more similar. I would say that this structure is more similar to the structure of a glass module than that of a conventional glass foil module. And I just have one more slide about this work, and it's the main outcomes of this work, which I will recall here. So what are the lessons learned from this work, which as said, it's a nearly 40 years old technology now. And in a temperate climate, we can say that really more than 70% of the module would satisfy a warranty set at 35 years, referring to an 8% of the initial value. The degradation rates were strongly correlated to the quality of the encapsulant used. You can see three different visual appearances of the modules after 35 years of operation. And some were really transparent and clear, nearly as new. Some were a set of modules was partly yellowed, and another subset of module was very browned. And the behavior of the encapsulant was pretty much reflected to the degradation rates of the PV modules, which you can see on the left-hand side. Another important issue, all these modules were laminated with the same encapsulant, which was PVB at the time, but these were coming from different suppliers. So another takeaway is that changing one single element in the bill of material can really have a very strong impact on the long-term performance of the module. And also another observation from this work is that the degradation rates tend to accelerate over time. So for quite a long time, they can be linear. We can have a linear degradation, but then when approaching the end of life, we start having, for some modules, not for everyone, yes, an acceleration in the degradation. So let's go back now to the technology of silicon heterojunction. This is a fairly new technology in comparison, so we do not have so much information or experience with this technology. And on the right-hand side, you see this chart, which is a well-known work from Jordan and colleagues at NREL, reporting different degradation rates found in the literature. This work is from 2013, but it has been updated a few years later. And now you can see that in this work, they are reporting for crystalline silicon these degradation rates, indicating that there is a median distribution of 0.5% per year in degradation. And of course, this is not a Gaussian curve, but it has a long tail towards higher degradations. And for the GoPV project, we have been collecting data published in the literature for silicon heterojunction solar cells and modules. This is what you can see in the left-hand chart. And we're also preparing a paper on this. And the works available were not many. It's only 12, 14 publications, but we were able to extrapolate 15 data points. And what you can see is that basically, if we take the median of this curve, it's a similar distribution. And again, we have degradation rates if we take median values, which are fairly similar to the ones reported by Jordan and colleagues in earlier years. So of course, the number of data points is absolutely not comparable. So statistics is missing, but we start having an idea of reported values for the silicon heterojunction technology. So ideally, if we assume a linear degradation over the years, basically, and I just mentioned before that this is not always the case, in principle, a 35 years performance warranty for this technology is realistic. Now, of course, this analysis comes with some caveats or multiple caveats. In general, this kind of analysis include all possible published data in the literature, which means very high quality data as well as low quality data, indoor measurements and outdoor measurements. Not always this work differentiate between degradation rates for modules or for systems. And of course, climate can also play a role. Whereas if we want to find any specific issue or caveats for the silicon heterojunction technology, of course, the track record for this technology is still limited. And so far, this analysis takes into account mostly modules from one single manufacturer, which was the first to enter the market with this technology. This is reflected from this chart, where the one on the left-hand side, where we are simply reporting publication year and the number of years of exposure in the field. So we see that most of these publications are really recent. Now I will jump to the next slide. And of course, in the literature, there is not really multiple failure modes which are reported for the silicon heterojunction technology, but in some cases, a loss in the open circuit voltage is reported. And this is in principle compatible with the loss of surface passivation properties. And another issue which is well known for silicon heterojunction cells or a potential weakness is that of the high sensitivity to water and moisture ingress. And this brings me to the last part of my presentation, where I will briefly talk about module structures for this technology. And of course, you see on the left-hand side the typical glass backsheet or glass foil structure for PV modules, where we have in principle on the rear side of the module a breathable or partially permeable backsheet. Or on the right-hand side, a glass-glass structure, which also, of course, comes with the advantage of allowing bifaciality of the cells, which is in principle a much more, much more robust structure, in principle, because it's not permeable to gases or moisture or oxygen. On the other hand, if we use glass backsheet structure, I think that in general, for this technology, which is really sensitive to water, we should use backsheets with moisture barriers. Even though I've seen some recently introduced silicon heterojunction modules on the market, which to me do not contain such a foil. Now, of course, the choice of encapsulant is critical. This is a table reporting different properties for encapsulant commonly used in the PV industry. And generally, as a potential weakness is that of sensitivity to water and moisture. Generally, we need, for this technology, we need to select an encapsulant which has very low water absorption properties or low WVTR, which is the water vapor transmission rate. And so generally the choice falls on a class of materials which is known as polyolefins or ionomers. Of course, these materials are more expensive and have also a lower track record compared to other materials as, for example, Now, as I was mentioning, the weakness of these technologies to water ingress, I will now try to say that, so these are some results of dump heat testing. On the left-hand side, you see a work published by a Korean group where they report the degradation of modules by exposure to dump heat. These were modules encapsulated with PVB. And as we have seen in the previous slide, PVB is not an optimal encapsulant for this technology. Whereas on the right-hand side, you see some results performed within the GoPV project at EPFL, where we were also using a non-optimal encapsulant. And you see the degradation. If you can have a look at this green curve, this is basically a dump heat test. Whereas the yellow curve is also, I mean, it's kind of a dump heat test with the addition of a negative bias voltage, which makes it a PID test, so potential induced degradation. So you see that really, if you have a look at the green curve, these modules were encapsulated with EVA, so it's also a non-optimal encapsulant. These were one cell mini modules, and really the technology was extremely sensitive to this. On the other hand, we have found that encapsulating glass-glass modules using an edge seal was able really to prevent the degradation in a very strong way. And I will not show this for dump heat, but for example, I will show it for PID. So this is potential induced degradation, which is according to the IEC standard. Generally, it's performed only for 100 hours. 96 hours in principle, by applying a negative or a positive bias voltage. And this is our mini module structures, where you can see that if we were applying a negative voltage, so really in a potential induced degradation test, the glass-glass modules encapsulated with EVA let me repeat that this is not an optimal encapsulant, was degrading very strongly. Whereas if we were using an edge seal, you can see that basically the performance, the long-term performance was very good. And this you can also see from this last chart where we simply report the degradation rates for the power, the current, the VOC, and the fill factor after 800 hours of test. So this is nearly 8 times the duration of the test foreseen by the IEC standard. And you see that if we are using the orange bars, it's glass structures, the green bars, it's glass structures reinforced with the use of an edge seal. And you can see that really the use of an edge seal was really mitigating and preventing the degradation. And as said before, we saw exactly the same results for dump pit tests and also in other tests. So this really tells us that in principle it's possible also to use different encapsulants which are maybe less suitable for the silicon heterojunction technology, but using an edge sealant, or at least using an edge sealant would allow us also to use different encapsulants. Now I come to the conclusion of my talk, and it's, well, first of all, we have shown that 35 years of service lifetime of PV modules deployed in temperate climates have recently been demonstrated, even though this was a conventional BSF crystalline silicon technology. We're also performing a survey on published data of long-term degradation rates for the silicon heterojunction modules. And we have seen that these degradation rates, even though the number or the statistic is not as based on such a high number of evidence and numbers, we are coming out with median degradation rates for the silicon heterojunction technology, which is compatible to that of conventional crystalline silicon. So minus 0.5, minus 0.6% per year, even though these numbers need to be finalized and confirmed. And if we are really assuming a linear degradation over the year, basically a 35 years performance warranty or lifetime for this technology is realistic. The published work and also findings in GoPV suggest that loss of VOC is observed, and this is in principle compatible with the loss of surface passivation properties, and that silicon heterojunction cells are extremely sensitive to moisture and water ingress. So this brings me to the last part of the conclusion. So that's really about reinforced module structures. Basically, glass structures seems to be okay. We need, of course, encapsulant with a low WVTR or low water absorption rates. And if we are using glass backsheet, possibly the use of moisture barriers are required. And we have seen that using edge seals with glass structures really provide an excellent resistance to moisture and water ingress, even when you're not using optimal encapsulant. Now, if you are interested to learn a little bit more about the silicon heterojunction technology, this is a book we've published at the end of 2020. I also contributed with a few chapters on module technology, but we have a dedicated chapter to silicon heterojunction cells. And this brings me to my, I would like to acknowledge all partners of the GoPV project at SEA, particularly Romain Soula and Stéphane Goyeret, for sharing silicon heterojunction solar cells, and my colleagues at PV Lab, particularly Olaz and Luca, who were performing much of this work. And with this, I'm done.
Thanks, Alessandro. Very nice presentation. Hopefully you're not done. I think there are a couple of questions and you can also answer some of them in the chat. Maybe one or two here directly oral. I think what, because you pointed out really this 35-year lifetime, which is great. We have now efficiencies of 30 years for glass and for at least for bifacial gas backsheets. We also have 30 so that they can compete actually with that option. So what was your experience? What's better, or have you seen any advantages for the one or the other in your research?
And what the one of the other
for glass versus glass backsheet modules, when you looked at them, actually, advantages for one or the others regarding reliability?
Well, I cannot really say, because in GoPV we are focusing on glass structure. Of course, the bifaciality is important. I can say that also in this work I presented in the first two slides, I mean, these were conventional crystalline silicon solar cells. As I mentioned, they were encapsulated using a very robust packaging structure, which to me, they had a backsheet, but the backsheet was sandwiched with really a metal foil, and also using an edge seal. So basically this module structure was resembling more that of a glass module rather than that of a glass foil module. And yeah, so this is just a general remark. So I really cannot say what is the status of so far. I would say that at least 90% of the modules deployed globally, at least for utility scale PV systems, have a glass foil structure. And we need to wait 30 or 35 years to know how these modules will behave.
Okay, maybe one quick question, and then the others maybe you can take them in the chat and answer them written. So can you share actually what edge seal you used?
It's a conventional edge seal, which is used for PV modules, which is available on the market.
Silicone based or?
No, it's PIB.
Okay, okay. Thanks. Okay, then thanks so much. And again, there's more questions which you please answer in the chat.
I will have a look.
Okay, super, thanks.